Alright, so we're going to start section 3. If you did well on the chapter 2 test, then what you're doing is working just fine. Just keep doing it. If you didn't do well on the chapter 2 test, we need to figure out why you didn't do well so that we can make that not happen for chapter 3. If you watched all the videos and did all the homework and didn't do well, then you absolutely should start coming to my office and letting me work with you one-on-one to make sure you understand the material, well enough to do decent on the test. If you didn't do all the homework and watch all the videos and you didn't do well on the test, that would definitely be something you should do for chapter 3. Also, you can always come and visit me if you're not just feeling that you're understanding the material. So we need a couple definitions to get started with section 3.1. The title of the section in section 3.1 is called Functions. And when I was a student, it was hard for me to understand the concept of functions, even though I might have been able to do okay on the tests that covered the material that relates to functions. I didn't really understand them so well. Hopefully I can explain things better than they were explained to me, but there's a chance that I can't. But whether you understand the concepts perfectly or not, hopefully I explain it well enough that you can do well on the test, kind of like I did when I learned functions. So the first two definitions, or the only two definitions that we're going to have in section 3.1, is relations and functions. And a relation is just a set of points or ordered pairs. And a function is a kind of relation. A function's a relation in which each point has a different x-coordinate. So relations are just sets of points. Functions are special types of relation. A relation's a function provided each point has a different x-coordinate. So on the next couple pages, I'm going to show you different ways that we could describe relations or define relations, and then we'll talk about whether the relation that's defined is a function or not. So this is an example of a way to define relations. Relations can be defined using set braces. Here are two different relations defined using set braces. The R sub 1, it means relation 1. And relation 1 is defined using set braces. And inside the set braces are ordered pairs or points. Relations are sets of ordered pairs. This is a set of ordered pairs. These are set braces, so what's inside it is going to be the set that defines that relation. This relation has the points 3, 5, 4, 1, 6, 7, 8, 3, and 3, 11. This is absolutely relation because to be relation, you're just a set of ordered pairs or points. A function is a special type of relation, and it's a special type of relation that each point has a different x-coordinate. The first relation that I wrote in example 1 here is not a function because I have 2 points that have the same x-coordinate. And to be a function, each point has to have a separate x-coordinate. So relation 1, it's a relation, but it's not a function. So relation 1 is not a function. Specifically, to be a function, every point has to have a different x-coordinate. This R2 in this example means relation 2. The subscripting 2 means number 2, and the R for me meant relation. And when I look at relation 2, I have the points 3, 5, 4, 1, 6, 7, 8, negative 2, 2, 11, negative 4, negative 8, 17, 24. When I look at relation 2 and I look at the points in relation 2, every single point has a different x-coordinate. So relation 2 is a function. It's a relation because it's a set of ordered points or pairs, and it's a function because each x is different. Generically, when a relation's a function, I usually just say the relation's a function. More appropriately, we could say relation 2 defines y as a function of x. And that just means that in relation 2, there's no point that has, there's not more than one point with the same x coordinate. So I'm going to use the words function and y is a function of x interchangeably. When I use the word function, I mean that no 2 points have the same x, and in this section I'll switch back and forth between saying function and y is a function of x. For our purposes, the word function means y is a function of x, and it means in a relation no 2 points have the same x. So the easiest, the most simplistic way to define a relation is using set braces, and it's not possible to define every relation using set braces, because to define a relation using set braces and listing all the points, you only can have a finite number of points. If there were, infinitely many points, I couldn't list all the points. Relation 1 and relation 2 are examples of finite relations. Because they only have a countable number of points. Relation 1 has 1, 2, 3, 4, 5 points. Relation 2 has 1, 2, 3, 4, 5, 6, 7 points. So these are examples of finite relations as opposed to infinite relations. So one way to define relations and functions is using set braces. And it's super easy if a relation is defined using set braces to determine whether the relation is a function or not, because you just look at the points. If there's multiple points with the same x, that relation isn't a function. And if each point has different x's, then that relation is a function. The second way that relations and functions can be defined or depicted is using graphs, and those kind of flopped onto the next page. So on the next page, I have 4 graphs, and let me get a little bit closer here. And each one of these graphs is just a set of points. This top left graph has 1, 2, 3, 4 points. That makes it a relation. This top right graph has 1, 2, 3, 4, 5 points. That makes it a relation. These are definitely relations, and these are finite relations because I could count the number of points that make up the graph. The bottom left graph is an example of an infinite relation. Notice I didn't mark any points on the graph, but any points on the graph that I can make a dot, like there's the point -3, +1, there's the point -4, 0, there's the point 0, 2. Any place that I can make a mark on the graph is a point that's part of that relation. And I don't have to make my points on the integers. I can make points on fractions, and there are, in some sense, infinitely many dots I can make on this graph. So this relation would have infinitely many points, because any place I could make a dot on this graph would be a point that's part of the relation. And I can make my points really small, and the more precise my pen is, the smaller I can make my dots. I could make infinitely many dots, so it would be impossible to list all the points like it was here in these finite relations. This would be an example of an infinite relation. When the points of a graph are connected, you get an infinite relation as opposed to a finite relation. These top 2 graphs are still finite relations because the points weren't connected. I can tell you what every single point of the relation is. This is another example of an infinite relation. The question we're going to be asked is which of these 4 relations represent functions, And in the top two, because they're finite relations, it's easy to determine if they're a function or not with the knowledge that we already have. The bottom two, because they I don't have the points listed, it's a little clunkier to figure out whether the relation's a function or not. So let me talk through each one of these four graphs to help you figure out whether the relation that's depicted is a function or not. The first relation in this upper left, I see the point -7, -5, -3, -4, +2, +3, and +5, +2. So let me maybe call this relation 3. This relation has the points -7, -5, -3, +4, +2, +3, and +5, +2. If I look at each x coordinate is different. This relation is a function, or we can say for this relation, y is a function of x. So it is a function. Or we can say y is a function of x. We're going to use interchangeably the words function and y is a function of x. They're going to mean the same things for us. So for this relation 3, we can say this is a function or y is a function of x. This next relation I'm going to call relation 4, and that relation has the points -7, -5, -3, -4, -3, +4, -3, -6, 2, 3, and 5, 2. It's a finite relation, so it's possible to list all the points. And this relation's not going to be a function because it has 2 points that have the same x. So we can say this one's not a function. So for finite relations, I don't need any special skills to figure out whether the relation represents a function or not. I can look at each one of the points. If each one of the points has a different x, then that relation's a function. If there are more than one point with the same x, then that relation's not a function. The next two infinite relations, it's impossible to list all the points because there's infinitely many points, and some of the points I can't even approximate because they're ugly decimals. So I need to find a way to determine whether these graphs are the graph of a function or the graph of not a function. They're both the graphs of relations. And to determine, when you're given a graph of an infinite relation, to determine if the graph's a function or not, we do the vertical line test. Specifically, if it is possible to draw a vertical line to touch the graph in more than one place, then the relation is not a function. On the other hand, if it's impossible to draw a vertical line to touch the graph in more than one place, or if it's not possible, if it is possible, if it is not possible, to draw a vertical line sorry about my poor writing there. I was talking and writing and not writing everything I said. If it is not possible to draw a vertical line to touch the graph in more than one place. Then the relation is a function. So when we have graphs of relations that all the points are connected, the easiest way to figure out if that graph represents a function or not is just to draw a vertical line physically or fictitiously. If you can visualize a vertical line that can touch the graph in more than one place, then the relation's not a function. It's kind of easier to show that. The second bottom graph here, which I might call relation 6, this would be relation 5, relation 6, this relation would be considered not a function. Very specifically, I can draw a vertical line that's going to touch the graph in more than one place. So this relation, might call it relation 6, is not a function, because it fails the vertical line test, meaning it's possible to draw a vertical line to touch the graph in more than one place. This relation's not a function. The reason it's not a function is because the vertical line that I draw that touches the graph in more than one place, every place where the line touches the graph produces a point on the graph. This vertical line touched the graph at the point 5, 3, and it touched the graph at the point 5, -3. What I do when I draw a vertical line to touch the graph in more than one place, I'm finding 2 points on the graph that have the same x. So this relation has the points 5, 3, and 5, -3. Those are 2 points that have the same x, so it's not a function. The relation, I guess we'll call it relation 5, no matter what vertical line I draw through the graph of relation 5, it won't ever touch the graph in more than one place. It's impossible, it's not possible to draw a vertical line to touch the graph in more than one place. So this relation is a function. So this one is a function, or we can say y is a function of x for this relation. And again, I'm going to use those interchangeably, saying something is a function or y is a function of x. Are interchangeable. They have the same meaning to me. So that should be enough to get us started with the first, well, no, it shouldn't be enough. I haven't done it part 3 yet. Sorry about that. I was anxious to get going. The third way that relations can be defined, so relations can be defined as sets of ordered points. Real easy to tell whether they're functions or not. Duplicate points with the same x, not a function. Every point with a different x, they are functions. Relations can be defined graphically. Finite relations defined graphically. You can just look at all the points. If any points have the same x, it's not a function. If all the points have different x's, it is a function. I could have done the vertical line test with these finite relations. The only vertical lines that can touch the graph are the points of the relation in this graph are those 4 vertical lines, and none of those lines go through more than one point. The lines that I can draw that go through the points of this next relation are those lines, and this line goes through 2 different points, which means it's not a function. So I could have used the vertical line test on these. Anytime we're given the graph of a relation, the vertical line test is a way to determine whether that relation is a function or not. If it's a finite relation, it's easier for me just to look at the points. If I see every point has a different x, it's not a function. If there's points with the same x, if every point has a different x, it is a function. If there's points with the same x, it's not a function. When we have relations that are drawn with the points connected graphically, those are infinite relations because there's infinitely many points. If the graph fails the vertical line test, meaning you can draw a vertical line to touch the graph in more than one place, it's not a function. If it passes the vertical line test, meaning it's impossible to draw a vertical line to touch the graph in more than one place, it is a function. So the last way that a relation can be defined is with an equation. And if I have an equation that's solved for y, I can determine real easily whether these relations represent functions or not. The top relation, y equals 3x plus 8, if I wanted to figure out if that's a function or not, I can just graph the function y equals 3x plus 8, do zoom standard. And when I graph that function, it graphs to be a line. It has a y-intercept of 8 and a slope of 3. So the graph for this relation that's defined as an equation looks something like this. And this graph is going to pass the vertical line test, because very specifically for this graph, any place I would draw a vertical line, it would only touch the graph in more than one place. So this relation, y equals 3x plus 8, is a function. Or we can say y defines y as a function of x. So the third way that we can define a relation is just with an equation that has an x and a y, or an equation that has function notation, but we're not quite ready for that. This one is a function because the graph passes a vertical line test. This equation with the plus or minus sign, if I want to graph it, I have to graph it in stages. I have to graph a y1 equals the positive square root of x plus 5, and a y2 equals the negative square root of x plus 5. If I wanted to know whether this relation was a function or not, I can just graph it. Go on my calculator, do y1 is second square root of x plus 5, and y2 is negative second square root of x plus 5. And when I graph this, I get something that looks like that graph, a lot like that graph. And this graph, if I want to know if that was a function or not, it would not be a function, or y is not a function of x, because it fails the vertical line test. Alright, so that's a 20-minute introduction without doing a single problem. That's probably not the best way to get started on this, but it is what it is. We need that preliminary knowledge to do the problems. And now I'm going to jump into the problems in section 3.1. There's at least going to be 2 parts to this video. There could be 3 parts. So, the first 6 questions in section 3.1 give me relations that are unnamed relations, and they ask me the question, which of the relations define y as a function of x? And I put a hint here. A relation is considered a function of x, a function if each x is assigned to one y. That is, the relation is not a function when there are 2 distinct points that have the same x coordinates but different y coordinates. So for these 6 relations, I either need to say they are a function or they're not a function. And this is something that we just did, so hopefully this is easy. So I'm going to go to problem 2 and figure out if it's a function or if it's not a function. To figure out if a relation's a function, when it's defined as a set of points, I look at the x's. If all the x's are different, we say that relation is a function. So in problem 2, I'm going to say the relation is a function. And that would be the answer that I would write for problem 2. If I want to, I could say y is a function of x. And again, I'm going to use those interchangeably. They'll have exactly the same meaning. And because this is easier to write, that's what I'm generally going to write. So you should be able to do maybe all the problems between 1 and 6. I'll do all the even problems. So for each one of these problems, we just need to determine if the relation's a function or not. I look at the x coordinates of the points. I just had a hiccup in my video. When I move down to number 4, I look at the x coordinate of the points. If each x coordinate is different, then that relation's a function. Because each x coordinate is different, this relation's a function. So I'm going to say this one is a function as well. And I could have said y is a function of x. So both of these would be okay answers. To problem 4. And when I move down to problem 6, to figure out if that relation's a function or not, because there's 2 points that have the same x's, we're going to say this relation is not a function. Or we could say y is not a function of x, but that again, that's getting to be overkill. So that's problems 1 through 6. The next group of problems are asking the same question, which of the relations define y as a function of x, but instead of giving you the points, the relations written in point notation or set braces, it gives me a graph of the function. So problem 7 through 12 says use the vertical line test to determine whether relation defines y as a function of x. And then I just added what I already talked about. We say the graph of relation is the graph of a function provided it passes the vertical line test, meaning it's not possible to draw a vertical line that touches the graph in more than one place. So the vertical line test basically says if you can draw a vertical line that touches the graph in more than one place, then it's not a function. If it's impossible to draw a vertical line to touch the graph in more than one place, it is a function. So for each of the problems between 7 and 12, our answer is either going to be this is a function or this isn't a function. For your problem 7 fails the vertical line test because it's possible to draw a vertical line to touch the graph in more than one place. So we're going to say this is not a function. Or we can say y is not a function of x by just saying it's not a function. And for my problem 8, I can't visualize a vertical line that can touch the graph in more than one place. So for problem 8, for my answer, I'm going to say it is a function. And again, anytime I say something is a function, I mean y is a function of x. But I'm going to dispose with that notation, I think, from the rest of this video. And I'm just going to start saying it either is or isn't a function. So the next 4 problems that we have ask the same question. I just look at those graphs and figure out if they're functions or not. Problems 9 and 10 are tricky because the graphs fail the horizontal line test, meaning it's possible to draw a horizontal line to touch the graph in more than one place. That has nothing to do with determining whether the graph is a function or not. So to figure out if my graph is a function or not, if it's possible to draw a vertical line to touch the graph in more than one place, then it's not a function. If every vertical line only touches the graph once, then it is a function. Every vertical line for number 10 that I can draw only will touch the graph once. This will be is a function as opposed to not a function. Your number 9 is similar to my number 10. Your number 11 is similar to the number 7, so hopefully you could do that. 12 is the icky one. 12, off to the sides here, the far left and the far right, it's clear that you can't draw a vertical line to touch the graph in more than one place. The question would be what's happening around the origin here, and the window I picked for this graph isn't the best window. It's not supposed to be possible. This line that goes through the graph right through the origin is only supposed to touch the graph in more than one place. This is supposed to be is a function. I wouldn't ask this on a test because if you thought that this line that went through the origin touched the graph maybe there and there, you could say it's not a function. And it's such a poor graph that I'd have to kind of live with your answer if you thought it touched the graph in more than one place with a line going through the origin. I'd live with that as an answer. But when I wrote the problem, the function that I wrote, it isn't supposed to be. It is supposed to be a function. It's supposed to pass the vertical line test. The last group of problems from this part of the video give us relations written as equations, and we're supposed to determine whether the equation defines y as a function of x. And my hint is just do a graph. Solve the equation for y if it's not already solved for y, and sketch a graph, and then we'll determine if it's a function by using the vertical line test. So let me do problem 14, figure out if 14 is a function or not. I'm going to graph problem 14 on my calculator, just graphing x squared plus 4. I'll hit my graph button. It gives me just a nice generic parabola, looks something like that. And that parabola passes the vertical line test. It's impossible through that parabola to draw a vertical line to touch the graph in more than one place. So for problem 14, I'm going to say this is a function. And you'll do the same for 13. Problem 16, the graph is kind of strange because it has an asymptote in it, but let me try to do 16. I'm going to graph the function 5 divided by x, and the function 5 divided by x has a left half and it has a right half. So I'm just kind of copying what my calculator gave to me, and I have to ask myself, is this a function or not? And I claim that this is a function because no matter where I draw a vertical line through this graph that my calculator gave me, I could only touch the graph in one place, and that makes it a function. It's impossible to draw a vertical line to touch the graph in more than one place, so that makes it is a function. For 17 and 18, I'll do 18 while you do 17. For 18, I do second and x squared for square root, and then x minus 2, graph it. It's a half a parabola on its side. Looks something like that. And that clearly passes the vertical line test. There's no way to draw a vertical line to touch the graph in more than one place. So we're going to also say this is a function. Or we can say y is a function of x. (20 and 19 are kind of like that graph that for that problem 12 that was kind of tricky. So to graph number 20, I have to hit my math key, which is right under the alpha key, kind of under the second a little bit. Go down to option 4 that says cubed root, hit enter, and now I'm going to type x minus 5. So x minus 5, close my parentheses, and do my graph. And the graph looks something like this. Let me do it in a different color. It looks something like that. And that is supposed to be the graph of a function. There isn't supposed to be any place where it's clearly obvious that you can draw a vertical line to touch the graph in more than one place. So for problem 20, I'm also going to say this is a function, or again, I could say y is a function of x. The last couple problems, I can't graph on my calculator the way they're written because my calculator only can do a graph when an equation is solved for y. In order to do problem 22 to figure out whether it's a function or not, I need to solve for y. And so I'm going to minus x minus 2 squared from both sides without clearing the parentheses. And when I do that, I get minus x minus 2 squared on the left side by minusing it from both sides, plus 16 for the right side. And now I'm going to solve for y by square rooting, plus or minus square rooting. So y is going to equal to plus or minus the square root of negative x minus 2 squared plus 16. When I go to graph this on my calculator, I have to go y1 equals the square root of negative x minus 2 squared plus 16, and y2 equals negative square root of negative x minus 2 squared plus 16. This is going to make it not a function because I'm going to have to enter two functions to get this graph, and they're going to make it fail the vertical line test. So for this, I'm going to go y equals to second square root negative parentheses x minus 2 squared plus 16, close out the parentheses, and then negative second square root negative parentheses x minus 2 squared plus 16, and the parentheses. So I have two sets of parentheses. The x minus 2's in a parentheses and the whole square root. The square root starts and ends with a parentheses. When I hit my graph button, oh, that's kind of surprised me. I get something that looks like kind of a football shape. And I think the graph's supposed to actually touch the x-axis here, but it doesn't. It kind of doesn't matter. I still fail the vertical line test. It's possible to draw a vertical line to touch the graph in more than one place. So the relation defined in problem 22 is not a function. Your problem 21 is going to be a lot easier to deal with than my problem 22 was. For problem 24 and 23, I'm going to rewrite my problem 24 as y squared equals x plus 2. And again, to graph this, I need to solve for y. If I introduce a square root into a problem that doesn't start with a square root, I have to tag a plus or minus sign next to the square root. And when I go to graph this on my calculator, I'm going to do y1 equals the square root of x plus 2. And y2 equals negative square root of x plus 2. That's going to make this fail the vertical line test. Anytime I have to have a plus or minus sign when I'm solving for y, you're automatically not going to have a function. So I'm graphing both of these functions, y1 and y2. I look at the graph best I can, and it fails the vertical line test. I can draw a vertical line that touches the graph in more than one place. So I entered y1 equals the square root of x plus 2, y2 equals negative square root of x plus 2, and this one's going to be not a function. Or we can say y is not a function of x. Your 23 will work similarly. And we have one more problem for this part of the video, then we'll move on to a part 2. So 25 and 26, I need to graph these to figure out whether that relation's a function or not. To graph these, I'm going to solve for y by minusing 5x squared from both sides. I kind of want to write the 5x squared second. I think it'll make it easier to do the algebra that I need to do. Still haven't solved for y completely. To finish up solving for y, I'm going to divide both sides by 3 and get y squared equals 25 over 3 minus 5x squared over 3. And then I'm going to square root plus or minus square root. That immediately makes this not a function. Usually if a relation has a y squared, then that relation's not going to be a function. To graph this, I'd have to do y1 equals the square root of 25 over 3 minus 5x squared over 3, and y2 equals negative 25 over 3 minus 5x squared over 3. That's a mess to enter, but I think I can do it. So clear, clear. So y1 is second square root 25 divided by 3 minus 5x squared divided by 3, close my parentheses, and then y2 is negative second square root 25 divided by 3 minus 5x squared over 3, close my parentheses, hit my graph, and I'm going to get something that should fail the vertical line test. So clearly this fails the vertical line test. I'm skeptical that my calculator didn't graph it perfectly because the graph probably should touch the x-axis, but it doesn't, but it still fails the vertical line test. So for 26, I'm going to say it's not a function. Alright, so I'm going to pause the video and then we'll move on to the rest of the section in a part 2.